The next paper is latent factor models and aggregation operators for collaborative filtering in reciprocal recommender systems, presented by James Neve.
Okay, hello, my name is James Neve. I'm a first-year PhD student at the University of Bristol, and today I'm going to talk about latent factor models and aggregation operators for reciprocal recommender systems. And before I was a PhD student, I was working for a number of years in Tokyo for the largest online dating service in Japan called Pairs, which is part of Match Group. And I'm a very big advocate of online dating. I met my wife online, I've got a number of friends who have met their partners online, and I think it's therefore a great shame that reciprocal recommender systems is a rather overlooked field within recommender systems in general. Reciprocal RecSys hasn't really progressed past nearest-neighbour implementations, and I hope during my PhD to be able to advance this field and expand the literature a little bit and incorporate some techniques from general recommender systems into reciprocal RecSys. So, the main difference between reciprocal RecSys and standard user item recommender systems is that in reciprocal RecSys we have two users, and therefore we need to look at the preferences and properties of both users. So the standard method of doing this is to take a user item recommender system. For example, with two users, user A and user B, we'll look at the likelihood that user A will like user B, the likelihood that user B will like user A. We'll aggregate these two preference scores into a single reciprocal preference score that hopefully indicates how much these two users are likely to like each other. So, the original contribution of this paper is threefold. Firstly, because up until now, nearest-neighbour methods have been prevalent in reciprocal RecSys, I wanted to apply latent factor models to reciprocal recommender systems, which have been very successful in user item recommendation. Secondly, I wanted to be able to do efficient recommendation for large datasets. Previous reciprocal RecSys have mostly been done on hundreds or thousands of users, perhaps because online dating data is very difficult to get hold of. We had 10 million users at our disposal, so we wanted to be able to do that. And we wanted to look at different aggregation functions for combining the two user preferences into a single score. Previous papers have mostly used the harmonic mean with no particular justification, so we wanted to explore other functions and see how they performed in general. Our collaborator, as I've mentioned before, was Pairs in Japan. We have about 10 million users, it's the largest dating site in Japan, and it's part of Match.com, the group. If you're looking for a Japanese girlfriend, please try Pairs, it's very, very good. And just to talk a little bit about the user flow on Pairs. Usually, as on many dating sites, Pairs users start by searching for keywords they might like, cute animals, heavy metal, and so on. They find the user profile that they like, and they press the like button. The user who is liked gets a notification, and then they can either like back, in which case it's a match, or they can note, in which case it's not a match. And the note is actually very useful to us as data scientists because unlike many online dating services, this gives us negative preference data. After matching, users can message each other, they can arrange to meet each other, and of course, this shows us that, online dating, the success criteria is very vague, right? With Amazon or Netflix, if the user buys an item, that's success. But with online dating, is success a match? Is success a meeting? Is success marriage? If a marriage ends in divorce, is that still success? And so on. So, obviously we can't follow users throughout their whole lives. We have to pick one of these as our evaluation criteria. And numerically speaking, match is the easiest to do. And if users match more, they were likely to have more meetings and so on. So we use match as our success criteria. Just to talk a little bit about the technical system architecture, in terms of creating the models, it works about as you might expect. We create two preference matrices, showing the preferences of male users for female users, and the preferences of female users for male users. We use these to train two latent factor models based on how much male users will like a female user and how much a female user will like a male user. And we can then use these to generate a reciprocal preference score based on two preference scores, one for how much a man will like a woman and how much a woman will like a man. In terms of the preference aggregation, we wanted to look at a number of different functions and see whether that has a significant impact on the results. And in the end, we decided on 4 functions to examine. 3 of them, the arithmetic mean, the harmonic mean, and the geometric mean, are the Pythagorean means, and they're very simple mean functions. And we decided to look at these because this has never been done before, and we wanted to present a general exploration. We also decided to look at one more function, the cross-ratio uninorm. And we decided to do this because the cross-ratio uninorm has a property called the full reinforcement property, where very low scores, or scores that are quite widely separated, are heavily penalized and will give a result below either of the original 2 inputs. And this is called conjunctive behavior. And at the top end of the scale, 2 very high scores will give a result that's above either of the 2 original inputs, and that's called disjunctive behavior. And intuitively, this seems like it might work well, because if I really like a girl, the girl really hates me, that's unlikely to be a very good match, right? But if 2 people moderately like each other, that's potentially a match. So we want to penalize this wide separation. In terms of training our model, we looked at, we trained our model and we evaluated it against the previous best nearest neighbor solution, which was called RCF. I'm just looking initially at the aggregation function-based results. We've got RCF on the left and our latent factor model, LFRR, on the right. And in terms of RCF, the results are quite distinct based on the 4 aggregation functions. So the harmonic mean and the cross-ratio uninorm perform very, very well, and the arithmetic mean and the geometric mean perform less well. And we consider that this might be because of this property that both the harmonic mean and the cross-ratio uninorm have of penalizing very widely separated results. On the other hand, in the case of LFRR, the results are slightly more confusing and we think need more exploration. The cross-ratio uninorm performed particularly badly, perhaps because of the jump between averaging behavior and disjunctive behavior at the top of the scale. Comparing the 2 algorithms directly in terms of F1 score based on cross-validation, RCF and LFRR, using their best aggregation functions, actually performed the same. So both of them had 0.87 results. And this may not seem very satisfactory, but actually, in terms of efficiency, LFRR far outperformed RCF. LFRR was able to generate results for up to 10 million users within reasonable time, whereas RCF, being a nearest neighbor-based model and operating entirely in memory, was unable to generate results past about 100,000 users. So in conclusion, aggregation functions do have a significant impact on the outcome of reciprocal recommender systems, and we consider that this needs more research to determine exactly what impact these have and what's the best choice in terms of different reciprocal recommender systems. And latent factor models, at least in terms of the one that we decided to train, produce similar results much, much more efficiently. So in terms of large online dating sites or social networks, we consider that this might be a good solution. In future, as I mentioned, we'd like to look at alternative aggregation functions. We'd like to look at potentially other methods of training latent factor models in terms of more advanced, and we'd like to look at potentially single-sex dating, which is a rather different problem because of the single class of users instead of being able to separate into male and female. Thank you.
Could you raise your hand?
Well, thanks for the talk. I'm wondering about one of the sort of well-known phenomena in the online and reciprocal recommendation world, which is differential attractiveness, the idea that some users will get way more messages than others, and I'm wondering how you sort of take that into account. It seems that there isn't perfect symmetry between the two users.
No, well, in terms of popularity, it is certainly a problem in online dating. In this case, because we wanted to specifically test latent factor models against nearest-neighbour implementations, we didn't do anything complex on that. But I believe that last year at RecSys, Akiva Heinemann presented a paper on a neural network that evaluates user popularity. And potentially we could also implement that into this system as a post-processing of the results and weigh user attractiveness as part of the equation.
To pose that question, there's a paper by Mark Newman using networks to rank attractiveness, but that's not my question.
Okay.
My question is necessarily a non-match a failure? Because I suspect that in dating websites, you want to see what's out there before you actually know what you like. So perhaps you will be willing to tolerate more non-matches just to see what the field is like before they decide to solve.
Okay, no, that is an interesting idea, yeah. And I think presenting a variety of users, even users who might not necessarily match, is certainly a positive thing in an online dating environment. In terms of having relatively simple evaluation criteria, in being able to do offline evaluation, using match as a success criteria seems like the best result. But we would very much like to test this online and to look at the effects that a greater variety of users compared to just the best users would have.
Thank you so much for the talk, it's really interesting. My question was about if you have tried to evaluate by looking at single-sided recommender systems, where you potentially try to optimize probably for one step further than just if the match is happening or not, as in like you send a match request or something and whether it gets accepted or not.
Sorry, can you repeat that a little bit?
As in, I mean, you're talking about like signals like or something like that, but potentially there is a signal from the other side as well, right? So you can think of it as a handshake at the end of the day.
Yeah.
So if you try to optimize for the whole thing, that would be a single recommender system, not a reciprocal one, where it kind of tries to optimize for the same objective. I was wondering if you have thought about those lines.
Yes, yeah. The tests we did were based on matches, which are two sides handshake type things.
Yes.
So both users like each other. So that was our success criteria.
No, I was trying to ask if you try to is it possible to optimize it directly from one side of the recommender system rather than having like...
Oh, I see, optimize instead of having two separate recommender systems. So far that hasn't been done as far as I know, but if you have any ideas how it could be done, I'd be very interested too.
Thank you.
Thank you.
So I have a question about whether the outcome variable was the same, right here, whether the outcome variable was the same for men and women. So were there equal numbers of likes and dislikes for men and women? And if not, if there was an imbalance there, how does that affect the reciprocal recommendation and the success criteria, I guess?
So in general, at least on pairs, I don't know how this affects other dating websites. On pairs, men tend to be more active in sending likes, and women tend to be more passive in waiting for likes. And that does certainly have an impact on the outcome, in that if you recommend a passive user to another passive user, it's unlikely that an interaction is going to take place. And that is certainly acknowledged as a problem in reciprocal RecSys. It would be very interesting to look at ways to tackle that. We didn't do that in this case, but I would certainly like to.
Thanks for the talk. I guess one concern I have with using simple aggregation functions like this is that if you look at it from a social choice perspective, there's a lot of incentive for users to potentially misrepresent their preferences. Do you see any evidence of this? And have you thought about if there's a need for more incentive compatible types of matching.
By misrepresent their preferences, do you mean specifically like other users in order to get certain recommendations?
Yes.
I don't think there would be too much motivation to do that because recommendations aren't the only thing on the site. Users can also search for what they like. But if you wanted specifically to get recommended to other users, I would imagine that the number of users who would do that would be fairly small in terms of the total number of users using the site. They would have to analyze how the recommendation algorithm works to start off with. And I think most users probably aren't aware of those kinds of intricacies. But it certainly is an interesting point and one that we should look at, yeah.
Okay, thank you very much.